Hello, hello. Welcome back to FutuCast, an English speaking episode or English version this time. My name is William von der Palen and Isak Rautio. Next to me, as usual.
Next to you, as usual, yeah.
Next to me, yeah. Hey, we're going to talk about quantum computing again. And we did one episode quite recently with in Finnish with Hermanni. So if you do speak Finnish or want to learn Finnish, go check that out as kind of a introduction also to this episode. We talked about how quantum computing
is a great way to learn Finnish for the first time. If you're learning
yes,
Finnish,
exactly.
It's an episode about
but that's kind of nuts and bolts of how it works. And today we have two industry experts, and we're gonna be talking about the kind of the broader ecosystem and implications for Finland and kind of the state of quantum computing, if you wish. So we're joined by Himadri Majumdar and Hassan Nasseri. Welcome.
Thank you.
Hello, thank you.
Do you want to tell our listeners who you are and what you work on, kind of to give some background?
Go ahead, Hassan.
Himadri, okay, I will go. Yep. Hello, everyone. I'm Hassan Nasseri from Accenture. We have a global technology innovation group, and we have a team for quantum computing that I'm leading the research activities there globally, as well as business experiments with different clients across the world. I have been in Finland for last 3 years with Accenture and working on local ecosystem with Himadri and everyone else. So, good, Himadri.
Thank you, Hassan. Hello from my end as well. Very nice to be here. My name is Himadri Majumdar. As said, I'm the program manager for quantum programs at VTT. What it means is many different things. If I pick out a few things that I do in my day job, I'm managing the quantum computer build project that we are doing in Finland and VTT together with our partners IQM. And we just announced our 5-qubit quantum computer operational. We are still building the 20 and 50 qubit machines. Apart from that, I am very deeply involved with the ecosystem, just like Hassan said. So we are strengthening the Finnish quantum ecosystem, especially the business ecosystem, because quantum computing is a new thing, quantum technologies is a new thing, and we want businesses to learn and understand what are the possibilities, what enormous capabilities and potential this has, and how they should get ready for the future, how it can impact their business and take advantage of it. So that's another role, and I also extend that role into the European domain. So I'm the Finnish country representative in the European quantum business community, and there we discuss about different issues regarding quantum computing on the European level. And again, it's one of the very key topics of emerging technologies for Europe as well. So that I think summarizes some of the things that I do. Very nice to be here again. Thanks.
Thank you to both of you. Yeah, after the Hermanni episode, which I agree with William, you should definitely listen to it, listeners, if you still haven't, if you want to get an introduction of it. There's probably also good English language introductions to quantum computing. But I got very excited about the technology, and it's very nice to hear that there's apparently an ecosystem in Finland that's been built around this. And I get this is a question to both of you, but I guess Hassan maybe should start with this one. What is this ecosystem like? Who is in it, and what's going on with it?
Yeah, okay. Actually, probably Himadri is a better person because he is more or less, he is very focused on Finnish ecosystem. But I can tell you a little bit about more broader activities that we have
done. Sorry about that, Himadri.
The ecosystem. No worries. So yeah, across Nordics, we had few activities together with some vendors and partners, and there is a large ecosystem of both academic and industry from small companies like startups and going to also enterprise. So there is a large activity in Nordics, also across Europe and globally in this area. The amount of investments are very large and so on. I think we will talk about this more. But going to connecting with what is happening in Finland, currently, I think Himadri will tell us more, but VTT has a great role recently in this area of connecting all the businesses. What Accenture has been doing when we started this work, there was not actually an ecosystem at that time, and we gradually started connecting and having some events and so on. But today there is a good ecosystem. I ask Himadri maybe comment more on that. That was the current Finnish ecosystem.
Yeah, absolutely. Thanks, Hassan. I think that's exactly the point. That when we were, or let's go back a little bit. So, in end of 2020, when we announced that VTT and Finland is going to build its own quantum computer, it came as a sudden surprise to a lot of businesses, a lot of industries, and they were like, okay, what is it? Why are we interested in this? And there we realized, I still remember the conversation in the event with Hassan as well, that we need to educate. We need to tell people what it is about and how we can help them to understand it. And that sort of triggered the whole discussion between various stakeholders to formulate this. And that kind of eventually led to a Finnish ecosystem called Institute Q, which is the Finnish Quantum Institute. It's a virtual institute, but that's the overarching ecosystem in Finland, which covers education, research, innovation, business, policy making, educating the broader public, and so on. So we covered the whole kind of potential stakeholder in the society and community on that. And one part of it, of course, is the business community and the industrial community. But it is very obvious for us now that we bring in the whole community together and try to help them understand where we are going and where we are now, so that they learn and they understand it in the right way, that what potential quantum businesses can take advantage of. The business community is called Business Q. We started it officially towards the end of last year, October, I think. And Accenture was one of the founding members. So we were 6 companies who were the founding members of Business Q. And that now, since then, we have expanded to 20 companies. So it's really growing quite fast, and we expect to grow even more. The more the businesses learn about quantum computing, quantum technologies, the more interested they are getting. So it's a growing and evolving community in that sense.
And how does it kind of look from a business's perspective at this stage, when we know also based on the last episode that there are no really like or when we talk about quantum computers, we have some kind of vision in mind, and we're not quite there yet. And for businesses, that means probably that the like immediate applications and immediate things they can get out of it aren't there yet. So what are kind of the motivations for the businesses to be involved at this stage? Are they trying to learn and keep up, or are they funding the initiatives, or how does that kind of look?
That is exactly the point. I'm so hoping that this is a question for me.
Yes.
So, yeah. All right. So those are the points, of course, and it's a bit bigger than that, because there are several different angles that the businesses need to understand, and it's not just what is the technological potential of quantum computing, but it's also whether the people, because quantum computing is so radical, that whether the current workforce has the capability to adapt itself to quantum computing. So they have to prepare the workforce for future as well. And then there is the other aspect of seeing the business benefit of it, not just because it's doing it for the curiosity of it, but seeing the business benefit of that. And from that perspective, what we have been very successfully telling the companies so far is you have to think of it as a foresight and roadmap, that this doesn't happen tomorrow. It doesn't happen in a year or two. But the preparedness that you need to have is going into 5 to 10 years down the line. And that requires a planning. I mean, you cannot just abruptly change things in a IT environment. So if you want to take advantage of quantum computing, you start doing the foresighting. You start implementing small steps, doing small sprints, small experiments, and see how it can benefit you in that sense. So that, I think, all of these are important messages that we are trying to get across to the business community. And it is getting across, which is great.
Do you think, Hassan, that this this pitch sort of reflects itself in the business community, or what does it look like on the other side?
Yeah, that's I think exactly what Himadri said. So there is also one other dimension to it that I can add, but generally it's what Himadri said. The message is about readiness, and that's what we also do at Accenture, and it involves many different stages. Like it starts from just awareness, and some industries just want to know what it is and then what the impact would be, and then learning and building the talent and experimenting and so on and so forth. So building full-scale programs depending on, so that's the readiness part in the whole ecosystem. I think it's currently understood by many businesses, and we are getting there more and more, as you might say. But there is also one other dimension to it, which is, I mean, if businesses don't want something, that will not develop. And quantum computing is a huge and expensive challenge for the whole humanity to make it happen. So it cannot, like, businesses wait and it happens and use it. So there should be a demand, and I would say there should be even a hype. And so that's also other part of it. So businesses contribute by joining, by knowing, by telling what they need, so that the technology can develop to meet those demands.
Yeah, for sure. Yeah, supply or demand creates supply, even in this case, which is probably important to remember. And in this case, kind of consumer demand won't create the supply, because there's not that many people who will go to Gigantti and ask for a quantum computer yet. So I mean, that's not kind of the same driver as in vegetarian foods or something like that.
I do that because I like to confuse them.
Yes. Yeah, what's your latest quantum computer? Like, do you have the new Apple one? But yeah, no, but for sure, and also for for Finland, I think this kind of foresight and this kind of thinking is very welcome. So we kind of have a tendency in Finland maybe not to approach the future by doing things like this. So Finland could be a leader actually in quite many technologies, or at least show the way and create initiatives like this. But we've been maybe a bit, I don't know why it hasn't happened, but we haven't been that prone to doing that. And there's a lot of discussion now for Finland to find kind of the competitive edges for the future. So why do you think that Finland is a good place, and why is quantum computing one of the initiatives that is happening in Finland? Is it because of you guys and the great work you do, or is there like a bigger driver to this? Why Finland?
I can give it very quickly, and then maybe Himadri can continue on that, because Himadri actually knows probably more about the history of quantum computing in Finland than I do. But just back to your question, William, Finland is not a huge country, so probably looking for advantage or edge in all possible sectors is not feasible, and it will not happen. So finding some niche is needed, and then quantum computing can be one of these. Actually, Finland has a great position here. And I would say, even if the whole country does quantum computing, maybe it will be a huge business in future. I don't know, but that's somewhere that Finland has exceptionally good advantage currently. It's just a matter of, can Finland keep this and progress on that? And I will give it now to Himadri to tell you what is that advantage and why Finland is well positioned today.
Thanks, Hassan. I think that was an excellent point, and I totally agree. And it's also, I mean, having lived in Finland for almost 2 decades now, I think it's a societal mindset of trying new things and going towards new things and seeing what is the potential is a great mindset. I mean, Finnish engineers are known globally that they are great engineers because they are curious about new things. So that creates a sort of societal test bed, if you call it, to try new things. And quantum computing just happens to fall into that basket and makes it interesting. But there is a history as well. And exactly as Hassan said, that there is a long history of things that Finland has done very well and is now in very good position to take advantage of it. So if we go back, let's say 50 years or so, in 1960s, in then Helsinki University of Technology, or Aalto now, they started looking into a curious thing of how low temperature can they reproduce in the laboratory. So it's a curious experiment. And that started a whole research agenda on cryogenics or low temperature physics. So Professor Lounosma's effort from there has spun on and on and on, and that has created a global leading research in Finland on low temperature physics. So we are one of the global leaders on that topic. And that is a basis for doing quantum computing. If you don't know how to create good dilution fridges or temperatures which are 1,000 times cooler than the outer space, then you cannot do quantum computing, at least in some cases.
If this is confusing to you, by the way, go to that episode with Hermanni once again. Just a great point, because this is very central to how quantum computers work, apparently. Yeah.
Exactly. And this is what has led to companies like Bluefors and is now leading to companies like IQM. So they have a clear global advantage in technology. And that's something which we have in Finland. And it would be a shame if we don't take advantage of it. I think me and Hassan would like to claim that it's because of us, but it's not. So it's all because of the good things that has happened before us. We are just trying to make sure that the world knows about it and we take advantage of it. That's our role, basically.
What about the rest of the world then? And if we contrast it to the rest of the world, what is happening everywhere else? Obviously, the business perspective, I would love it for it to happen here. But as a technology, even just like, where is humanity with this?
I can say that humanity is very keen on this. And you can see from the global investments that are happening, or that has been happening over the last few years. And I mean, it's well known that the big giants like IBM, Google, Intel, they are investing. That's well known now. But it's also national investment. I mean, if you look at countries, China has invested huge amount of it. We don't know the number yet. India is investing 1 billion USDs in quantum computing. France is investing 1.8 billion USDs. Germany investing 2 billion in quantum computing. A country like Netherlands, which is not very big compared to Finland, is investing more than 500,000. Almost 700 million into quantum computing. So, and well, US, of course, I cannot leave that out. And there again, we don't know the total volume in US. I mean, we were in Colorado a couple of weeks ago, and the ecosystem there is mind-boggling. So there is a lot happening globally on quantum computing. So it's not something we are doing in isolation. Let's accept that.
Exactly. Is there kind of someone who is far ahead of anyone else, or as far as we know, is everyone kind of, virtually at the same stage? There's been some news from Google. I don't know if it's marketing or not. We're not into it enough to understand if there was like they achieved something. This is a very good quote. But yeah, like Google claimed that they had been able to run some very specific operation on a quantum computer that was seemingly impressive to tech people. So that's kind of like the best I can do on that. But is there kind of someone who is publicly very advanced in this? And there's maybe the question also that, do we think that there is some covert operations around this? There's been some speculation about also interests from governments, from China, from Russia, from the United States, from many countries in this, and some speculation about whether or not we know the whole extent to which we've been able to develop these computers yet.
Yeah, I think I can add some comments here. Is that there is this is a very big and long discussion, that there are all sorts of aspects of this thing, where we are, who is better than others, and what's happening. There is academic side of it, and then which is just the research. And then if you look at the building of the actual hardware, then it happens at different places. It happens in the industry, and also it happens in government labs. And then the other side is about the business algorithms and using this stuff. So there are different layers of the technology we can discuss separately. But I think now your interest was more knowing about actual hardware manufacturing of quantum computers.
Yeah, kind of the yeah, exactly.
So for that, at least there are two big areas. One is the government labs, which probably we will not know soon what's happening there. And it happens in US, it happens in China, highly classified information that we don't get much access to it. So if there is some covert operation, probably we won't know yet. But then there is other side of it, which is what industry has been doing. And some companies like IBM have been doing this for a very long time. They have been doing this for decades, not necessarily actively investing the whole time, but they have been in this area. Or, for example, AT&T Bell Labs. Bell Labs started researching quantum computing decades ago. So there is some advantage for some companies. IBM probably has now the largest number of computers available or built. But important thing about quantum computing to know is that yet things are not settled down. So we don't know exactly what would be the winning technology. And there could be just paradigm shift, and some company like IBM may lose the whole ground. I mean, we don't know. Of course, they are have a better situation now compared to others, but there is already several competing technologies. And even in single technology, which let's say superconducting qubits and this low temperature stuff, then even their architectures are varying. And it's not yet settled down how this thing will be built and scaled. So from background historical perspective, yes, some companies are ahead of others, but predicting future, I would say, is impossible now.
Exactly. Yeah, so there's kind of no consensus on how to build the best possible quantum computers. And as I recall from the last discussion also we had with Hermanni, they might also vary depending on the application they are built for. So there's kind of not one, in the same way we have now, basically all computers we use, personal computers, are pretty much the same. But that won't maybe be the case with quantum computers. There might be, like, there's no holy grail or one solution that fits everything.
If I speculate myself, I speculate towards building one holy grail. That's what our technology in the past have been. We always try to make one thing that does everything. It's easier, cheaper, scalable when we settle down on one thing. But it might be the case that we end up with different things, we can't say.
Yeah, I think the simplest analogy we can do is talking about Blu-ray player and DVD player. They pretty much do the same thing, but do it in a different way. And the same perhaps goes, maybe not in intricate detail on hardware, but the same thing happens in Apple and Windows in a way. So there might be two different platforms. You don't know. It's kind of unknown. And if we can try to compare with history, I think it's a good way to look at where computers were in the 1960s, when they were building a room filled with computers of ENIACs and so on. And they were custom-made computers for NASA and other applications. So that is where we are now at this point. And we are quite a distance away from personal quantum computers or personal computers, let's say. So.
Do you generally think that this might be a silly question, I don't know, but do whatever you want with it. But do you think the regular, normal, personal computer is a good analogy when thinking about how quantum computing will progress?
Well, I think that's what we have learned from history. So that would be a natural way of comparing where we will go and how we will evolve. But it might not be, because a lot of things we have learned and mistakes that we did with classical computers, we are not going to repeat those. So there will be a different approach, and it might be faster, that evolution of quantum computers. So, and we are hoping.
And also
for that.
looking at the, sorry.
No.
Also looking at the time scale of what Himadri said, I mean, that thing didn't happen in a decade. It took a long time, and maybe for half of the history of computing, at least like modern digital computing, it was not for personal use. So that could be for the quantum computing, that for some time it will not be in personal use, and then after that may change. And then by that time, we don't know where our classical computers will be. So it's really difficult now to predict that we will have quantum computer in our pocket or we will not.
But if we move on to kind of more concrete use cases, I think it's valuable to kind of understand, because for most listeners, and myself included, this kind of seems like a pretty vague thing. Like, we're building a more powerful computer, basically. That's what we understand so far. And we understand it might be a very big deal if we succeed on a big enough level at some point. But what are some of the use cases you guys are most excited about? And maybe we can divide that into kind of two different time horizons. So looking at the maybe near future, I don't know if that's kind of 10 years, let's have that as the near future, and then a little bit of a longer time horizon where we can more speculate on what can be possible. So if you, Himadri, would like to start with that.
Yeah, I would actually go a bit further into the future and let Hasan take the nearer future, because those are stronger business potentials, perhaps. Yes. But from a far into the future perspective, I would say it's more related to industries which has a strong infrastructure basis. So if you are talking about, for example, automotive industry, which needs a supply chain for battery materials or new types of battery materials, or if it needs or if you talk about the pharmaceutical industry, which needs to find new molecules and new materials for drug development. And then you can also think about topics like weather, climate change, or better prediction of weather or modeling of weather, and so on. So these are the things which would, to be very tangible, require a substantial amount of improvement in the quantum computing, let's say, capacity or strength. And that will happen in a time frame of 10 years, 5 to 10 years. And that will trigger the development of those applications. And that is where we'll come in. It doesn't mean, there is a strong caveat there, it doesn't mean that those industries should not be looking at it right now, because they can still take advantage of the low performance or reasonable performance quantum computers to see how the benefits are and where the benefits can be. But in terms of real applications or real advancements, that's where we are going. So, for example, I said to a student a few days ago that if you are tracking a tornado, and if you see a tornado graph, how it goes, they usually give a very wide place where it can hit. You don't know where it's going to hit. But if you can do better climate modeling or weather modeling, and you can say, okay, this is the 10-kilometer radius where it's going to reach, that would be fabulous and save a lot of lives. So why not go there with quantum computing in the future? Not possible now, but in the future.
I was going to ask you, Himadri, if you know any use cases for this. Did I interrupt you, Hasan? Sorry.
No, Himadri can conclude, and then I can go with shorter-term applications if you want.
Okay. If you would want to jump into one of your other examples, you mentioned supply chain, molecular engineering, a bit of a list there. Could we dive into one of those, one that you might think is particularly interesting?
Both are, and both have their societal impact. So I wouldn't choose one over the other. I mean, if you think of battery materials, we are now in a situation where we have a huge mismatch of demand and supply in battery and battery materials, and we are sort of relying heavily on one type of materials, and that causes a huge problem from a geopolitical and supply chain perspective. So if we can find, let's say, reasonably available materials that we can use for creating batteries, and if those kind of simulations can be done faster and material development can be fastened, the whole society benefits from that.
And am I right in assuming that the general idea is that the volume of the simulations is greater, and this is where the general benefit comes from?
You are absolutely. I didn't go into the details of that. Yes, that's correct. Because when you want to find a new material, the amount of computation you have to do to find a molecular structure or material structure that is suitable, it takes a lot of time in the current supercomputers. And that time you can save by doing a quantum computation with a reasonably powerful quantum computer. it doesn't mean that will change the timeline of the battery development as such, but finding the new material would become much faster.
Exactly. And if you look at the shorter term, like say what businesses can as you mentioned also, Himadri, that it doesn't mean just because it's not possible yet doesn't mean you shouldn't start engaging with this right now. So if I were a business leader in say, I had a battery factory or a pharmaceutical drug development company or something like that, how should I be approaching it, Hassan?
Yes. Okay. I think one thing that we can answer separately is that what makes a good problem for quantum computer. I'm not sure if this is covered in a previous podcast that you had, but Himadri slightly hinted that there are certain problems that are difficult to solve. First, we can identify those problems. And just to give one sentence here is that there are many problems that are not solvable today. And we don't even think that they can be solved. For example, if someone asks you, do you have a solution that can predict weather next year this day? I mean, it basically says that such a thing is impossible. And there are many of those examples. Like, for example, if a tornado. So a tornado is coming, so you can ask, will it hit my house or will not hit my house? So that kind of exact answer to those solutions are not possible. But those are maybe for a longer term. And there are many such problems that today we don't solve at all. We don't even try to solve them, because when we try to model them, we see that the complexity is huge. But then in near term, if we look at near-term problems, we need to look at the problems that match more closely to the architecture of a quantum computer. When we are converting a business problem to a quantum computer to solve, I assume, again, this is covered in your previous podcast, but one important thing is that quantum computers work differently from a classical computer. So there is an overhead in conversion. There is a step that we need to find an algorithm, and we need to match the problem to that algorithm. So the algorithm that we are using on a classical computer does not run faster on a quantum computer. So the step that we need to create a new algorithm can have huge overheads. And so there are certain problems that are more close to the architecture. And that is basically first intuition of building a quantum computer. I think it came from Richard Feynman saying that the nature is quantum. So if you want to simulate the nature, then you build a quantum computer. Because if you want to simulate the behavior of an electron, the overhead of mapping that to a quantum computer compared to classical computer is much smaller, compared to another problem that is completely in a classical world when you want to map it. So in near term, we see that there will be applications in quantum simulations. So meaning that if you want to simulate the quantum behavior of the material for physics and chemistry, you want to find the energy of a molecule, small molecules in certain reactions that are very important to simulate. Those small molecules could be, for example, fertilizers. You want to build a fertilizer, which is a small molecule, but you want to fully understand that molecule and find a path to make it with using lower energy or something like that. So those kind of exact simulation of molecules and chemistry is one of the near-term applications. Probably will be the first one that we will see quantum advantage. It's very likely. And as I said, the reason for it is that the problem, how it is formulated, maps much more natively to the architecture of a quantum computer. Then if we go look at other use cases outside chemistry, there are also so-called open quantum dynamics or open quantum systems. Means that you can use still the model of a quantum system to study systems that are not fully quantum, like you want to study photosynthesis, or you want to study some physical properties of the material, which is not fully quantum, but the quantum model can be applied to it or extended to that. And those are more like, again, applications that may come next. And that applies to the research in a new material and that sort of stuff. Then probably we will see applications in more like going from that step to more business applications. And the business applications, first ones or the largest area that we see will come is optimization. And optimization Ian Himadri mentioned supply chain optimization. And then depending on how large the problem is, some optimization problems can be small but very difficult. Some can be very large. The large ones will be for later, but the smaller problems, when I say small problem, the problem size can be small still, could consider 100 elements or something, but finding a solution could be still too complicated. May require 2 to the power of, for example, 100 steps, which is still larger than the age of universe. So there could be cases that we have small problems that are very complicated, and there exist many of those optimization problems. Then at different business sectors, they could be the next candidate for quantum computing. And we can, if needed, we can go through some examples of those optimization problems, but it's very difficult at the moment to say which one will happen before the other one.
Very, very interesting.
Yeah. One thing that came to my mind while listening to Hassan, and I think I completely agree with your analysis, and this sort of reminded me of what I was listening to Professor John Preskill, I think, a few months ago, and he was explaining it very nicely, that what we are doing with the quantum computers now in real time, in mid-term or shorter term, is solving problems which are classically hard but quantumly easy. So that's what we are doing now. But in the future, with 10 years and beyond, we'll be doing things which are classically impossible but quantumly hard. So we are getting one step at a time in that sense.
I think that's a very nice way to word it.
Yeah.
It makes total sense when you say it like that, and that gives hope also for the future in a way. One thing we didn't ask in our last episode, and I've been wondering about, and it's kind of, what is the relationship between hardware and software in a quantum computer? So if you basically look at a normal computer, the
Interface.
Hardware side seems pretty similar. You have like a certain amount of RAM, and you have a certain amount, certain kind of processor, and this and that. And then what kind of distinguishes these computers from each other is kind of, is it Windows, is it Linux, or is it Mac OS, basic for a normal user like us. That's what we see. And now some computer purists are twisting and turning and saying like the hardware is completely different in many computers, and I understand that. But basically, for a normal user, the software is kind of the key in many ways. What is the relationship in a quantum computer? What do you need to emphasize? It seems at this point we're really focusing on building the hardware side and figuring that out, but that might be the wrong analysis. But if you start, Himadri.
Yeah, I think there is a similarity, and the similarity again goes back a few decades back. When we started with programming the classical computers, all classical computers had their own operating system or own compilers and things like that. And this is where we are now with the quantum computers. Every quantum computer has its own compiler, has its own machine-level programs, and then you build the software stack, which is mid-level and high-level software stack. And at this moment, they are very problem-specific. So whatever you are trying to solve the problem, starting from the qubit design, you make the program accordingly. And there is no generic program as such. And this is, I think, if it was not mentioned, this is one of the things that IQM is very good at. And they are doing this co-designed approach with their customers or their potential customers to solve problems which are suitable for them. And I believe this is what will continue for some time. But there is another parallel business model, which is IBM's, where you can do a programming with the Qiskits and find solutions for different types of problems using their quantum computer in cloud. But I let Hassan comment on it, but I don't know if there is any generic operating system or that level of software that exists at this moment.
Yes, so regarding the hardware, I mean, the main difference is that compared to the classical one, as you know, and Himadri said, everyone, so that the hardware development is not yet standardized. And before hardware development is standardized, there is not usually huge amount of variations in the software. Okay, there are software, but those software are specific to each hardware. Mostly now there is each quantum hardware developer has their own stack. Once we get to a point that we have just one hardware architecture, then I assume there will be many software for that single architecture, and then we will see variations there. So that's currently the main thing. If I come back to the analogy that you said for the classical hardware, actually, I think if we look at the low-level technology, all our classical computing today is same hardware architecture. All of them are using more or less exact same silicon manufacturing technology. Even if you look at different CPU architectures, they can be manufactured in the same lab and with same building elements. So no matter it's an ARM CPU or it's an Intel CPU, it's built from the same building blocks. For quantum computer, it's totally different. It's totally different in a way that it's not even like a similar material. It's like one of them is built from completely different. One uses lasers, other one uses things. So it's a very different situation currently with quantum. And once we settle down with the architecture, and I'm assuming it will happen because one of them will win the scalability and the cost and things like that. Once we are there, then we will have operating systems and software developed for that specific architecture at large numbers. Currently, there are some efforts. The main type of effort that's happening now is to build software or a middleware that converts high-level code to multiple low-level hardware. So it basically maps different hardware architecture to a same middleware so that we can use different hardware with the same code. There are some standards under development. There is like OpenQASM, for example, or some other standards that they want to build some sort of a common assembly language for quantum computing. And that assembly language needs to be translated for each hardware so that it maps to that architecture. So there is a work at that level is still continuing now. Once everybody agrees on that assembly, I would say that that assembly language is also changing and new instructions get added. Some things happen every once in a while, and there are some new things that are supported by one hardware, not supported by the other hardware. But once that is fixed, then we will probably see more of a standard, what we can call maybe like operating system that works on top of that. There is some effort currently on building that kind of operating system. But since quantum computers are still in their infancy, let me tell you something that when you are building something generic, when you are building an operating system that works on different hardware, there is a lot of overhead for that. You are not making it very efficient for your hardware. When you are writing, let's say you are writing an assembly code, it runs faster than your high-level code. If you are running only one code on a computer, it runs much faster than running it on top of an operating system. So those all layers add extra overhead. And since the resources are very scarce in quantum computers and it's in its infancy, people are trying to get maximum out of them. So there is not much room to add those layers of luxury on top of the hardware yet.
Could you define, Hassan, middleware? What does that mean?
Again, this is not something very standardized, but there are different names that are used for what I refer to as middle names, circuit compilers or circuit accelerators, or there's also a company making what they call it quantum operating system. Or there is like term used circuit optimizers, for example, from CQC, or nowadays it's called something else, but they are making circuit optimizers. So there are like different names for a software package that receives your somewhat standardized quantum code and then creates a code for different hardware architecture. Because now we have 3-4 different hardware architecture which are common and getting more and more. Each vendor's architecture is slightly different. Their instruction set, if you compare it to a classical, their instruction sets are different. So you need this sort of a compiler to compile for that instruction set. And that compiler nowadays, there is a lot of emphasis in doing optimization. You know, classical compilers, we had compilers for a long time. We didn't think about optimizing the code. But with Quantum, again, the resources are so scarce that if we want to build a common compiler, from the first day, we start thinking about how to optimize that compiler for that specific instruction set.
I'm always amazed that we've gone from being literal apes to actually building stuff like this when listening to anything like this. It's pretty insane. Yeah.
And let me tell you one thing, which I found very, very interesting when I started looking at it from a business perspective, that what the businesses are doing. And I exactly as Hassan said, there is no one solution right now. And if you look at the brand owners, so for example, if you look at BMW, if you look at Bayer, and if you look at Goldman Sachs, these are three different industries, right? Finance, automotive, and pharma. And when they are doing their quantum experiments or their first quantum sprints, you always find that there are three set of companies involved. One is these companies which are the end users or brand owners. And then there is this company which is providing the hardware. So it can be either Quantinuum, which is Honeywell, ex-Honeywell, or it can be something else, IBM or some other hardware provider. And then the third leg there is the software company. So it's always this triangle of actors which are working together to find solutions. So I think this will continue for some time still. Like Hassan said, that there is no one solution that we have right now.
How approachable is this for, like, how big do you need to be for this to make sense? I'm thinking, like, is you mentioned that you can run something in the cloud, but we're probably talking still about quite expensive trials and sprints. This is not that approachable. Like, let's give an easy example. I have some restaurants in Helsinki, and we have big terraces. And I would like to make a weather model, a better weather model at some point, so I know how much staff to have there. I know this is not the reason we're building quantum computers, but this is like one reason for small companies to, if they were to understand the weather better, they would absolutely have a more efficient business. So, is there like any world where a small restaurant chain is able to use, quantum computing at this stage? Or are we still talking about, an asset that is more approachable to big business, such as BMW and Goldman Sachs? I'll give that to Hassan.
I can take that. The thing is that the restaurant owner is interested in the weather, but they will probably never think that they should predict the weather themselves. I mean, so there will be a person to predict the weather, and they can use it as a service. And the company who is predicting the weather is already using supercomputers today. So they already know that they have the need, and they already spend a lot of money. And for them, it's something, if that quantum is better or cheaper, they will switch. So it's already on their table that if there is a better solution, they will switch. The benefit to the restaurant owner will come with a new service that is better, but probably from the same provider or a new one, but it could be even from the same service provider. So if they are but one thing that will happen is that restaurant owner may see today's weather forecast not useful for them at all. It's too much error. It doesn't make sense. But with quantum computing, the weather forecast could be useful, could become useful, and they can start using the service for their business.
Exactly.
And that's what we think will happen for most of the end users or individuals, to find out that nowadays with quantum computer in the background, there are some new things that were not possible or not available, or all of a sudden as a magic, something happened. And now they have access to something that they didn't have access to it in the past.
Speaking of backgrounds, Hassan, is that behind you? What is that? Is that a quantum room?
This is from a lab. Yes, it was a research lab for quantum computing. It was for ion trap quantum computing research.
Wow.
Nice.
We took a photo of it in US.
I still have to add that it would be cool to have some quantum computers in our basement, but yeah, I totally agree that's the way it will go.
No, I mean, you don't need a quantum computer in your basement, but you can sit in your basement and you can play with a cloud-based quantum computer. I think you can still access IBM's Qiskits, and you can do some fun tests with that. You just need some basic programming skills for that, and not too expensive, if I remember correctly.
What a contrast that is also to, Bill Gates renting out the coding room or the computer room it will come a long way in 40, 50 years. It's quite a big contrast that I can go online and play with a quantum computer on the cloud.
That's how it should be, shouldn't it? I mean, we should democratize it, and we should give equal opportunities to everyone to have access and capability to try it out. So that's something which we should go for.
Exactly.
And I think as a governmental organization, what we are doing at VTT is exactly that. So we are trying to build a quantum computer which is accessible for the general public. So if there is, general public in the sense that there has to be some application defined for that, but it gives it access. It makes it accessible. So it's not something which is put in a stone wall somewhere or in a glass cage somewhere for somebody special to use.
Exactly.
What a strikingly fascinating episode.
I have one last question.
Of course,
I have to ask.
Absolutely, yeah.
One thing. Speaking about democratizing access and speaking about that kind of stuff, that also brings up one of the themes that is usually connected to quantum computing, which is the potential for malicious use. How do you view that? I mean, we've established on this podcast many times before that technology is not bad or good in of itself. So we don't have to go there. We kind of, that's been established. So it's not like the technology's fault that it can be used for malicious use. But how do you view this? Like, we've only now spoken about the potential for good, but there's obviously also potential for bad stuff. Maybe it's never nice to end on a negative note, but let's do it anyway, just to kind of have a reality check also that this is not, there is like maybe some actors that are interested also in using this for not so noble use cases. So how do you view that?
I suppose this would be for both of you.
Yeah. Exactly.
I can take it first, and I think you need another episode for that, honestly. It cannot be answered very quickly. But what I can tell is, I think you answered it in your comment that technology, it's not technology's fault. It's the user's fault how you do it. But that's not I think it's kind of a lame excuse in a way, but we need preparedness for that. So we know, for example, quantum computers, if they are sufficiently strengthened or capable, there is a potential that we can break some encryption with that, current day encryption with that. But that doesn't mean that it's the end of the world. We are developing encryptions which are quantum proof as well. So there has to be a solution for that as well. So it doesn't mean because of that threat we stop doing quantum computing. That's not the way to go. We find a solution to that problem, and whatever problem like that comes up. So that would be my very short answer to this.
I can add one just very generic answer to it, not related directly to quantum, but I can say that, okay, some technology could be potentially dangerous by itself, but computers by themselves, if you think of a computer in isolation, let's say that's the first computer that someone gave to you, it cannot be used for any dangerous purposes unless you have some use for it. Then someone can come and vandalize that use. So if you didn't use the computer yet, it's the first computer invented, I don't think so you can damage anything with it. So the idea that quantum computer can create some harm is because we think that computers will be used to create some benefit, and someone then can basically go and disrupt that benefit to humanity. But what I'm saying is that with quantum computer, there would be probably new benefits, for example, new cryptography and new advanced benefits. So it should not be more harmful or more dangerous than a classical computer, probably even less. As long as if we use it, then we will use it for also creating better cryptography, creating better security, and all sorts of other things.
Right. So it's a good way to think about it, like a new paradigm of threat and opportunity.
Exactly. Okay. Hey, it's been super fascinating.
Very, very fascinating.
Illuminating. We know now again 1% more about quantum computers than last time. So slowly getting there. But thanks so much for joining and sharing your perspectives.
Could not have gotten two better guests. Thank you.
Thank you very much for having us. Bye bye.
And thank you to listeners and viewers. See you in the next one. Bye bye.